Hello everyone. Today we will start with the distribution of electrons in the different orbitals. And to do so, there are certain rules, and we will study those rules today, right? And first of all, we have Paulis exclusion principle. Now, this principle states that no two electrons can have same set of all the four quantum numbers. So no two electrons can have same set of all the quantum numbers, right? So like here we take principal shell n is equal to 1, and for this main energy level the sub level is 0, which is S, and this S has only one orientation because ML can have values minus L to 0 to plus L. So this is 0, so 0. So one orientation means one orbital. One orientation means one orbital. So this one orbital can have two electrons. So those two electrons can have same value of n, that is 1, same value of L, that is S, same value of M, that is 0, but it cannot have the same, these two electrons cannot have same value of S, spin quantum number. The one should be plus half and other should have minus half. So from here we can say that it is clear that an orbital can have two electrons and they must have opposite spins, right? Now next is distribution of electrons on basis of quantum numbers. First of all, we will discuss the distribution of electrons in orbitals. Like here we take principal shell K, which is 1, which is designated as 1, and subshell is 0 for this because L have values from 0 to minus 1, from 0 to minus 1. So subshell will be 1 S. S comes from 0. Subshell named is 1s. So one orbital, one orientation. So two spins, plus half, minus half. So number of electrons maximum in K is equal to 2. Next is L, energy level second, principal energy level 2. And now here two values of L for this n value. One is 0 and other one is 1. 0 to n minus 1. 0 to n minus 1. So this subshell will be 2s, 2s, and the second one is 2p. 2 from main shell and p from L. So this is NL, 2p. Now for each L, ML have values minus L to 0 to plus L. So for this 0, L is equal to 0, so only one orientation. And for P, orbital P, it has three values, minus 1, 0, and plus 1. So three orientation means three orbitals, one orientation means one orbital. So one orbital means two electrons, three orbitals means two in each, so total 6. So 2 plus 6, 8 electrons are there in K shell. Now the next is M, subshell M. Now in case of subshell M, the principal shell number is 3. Now for n is equal to 3, L can have values 0, 1 and 2. It can have values for n is equal to 3. L can have values from 0 to n minus 1. Now for 3, values will be 0, 1 and 2 up to n minus 1. And for each value of L, ML has values from 0 to, so from minus L to 0 to plus L. For 0, it has only one value. For here, P. For P orbital, P subshell, the value of L is 1. So minus 1 to 0 to plus 1. So 3 orientations are there. And in case of L is equal to 2, minus 1, 0, plus 1, plus 2. So total 5 orbitals, 5 orientations. One orientation means one orbital. Now two electrons in one orbital. So only one orbital, 3s, with L is equal to 0. Now L is equal to 1, 3 orbitals, which are designated as 3p. So total electrons in 3 are 6. And similarly in case of D, the total orbitals are 5 now, because for D the value of L is 2. The value of L is 2. And 5 orbitals from minus, because ML has values minus L to 0 to plus L. So L is equal to 2, minus 1 to 0, 3 values, then plus 1, plus 2, total 5 values. So each value represents an orientation represents an orbital. And one orbital has 2 electrons, so 5 orbitals are total 10 electrons. So 2 plus 6 plus 10, 18 electrons are there in M shell. Right? Now next is relative energies of atomic orbitals. Now we have main energy shells, we have subshells, because the electrons in the main energy shells cannot have the same energy associated with them. So they differ in their energies, and those difference can be justified with the sub-energy levels inside the main energy shells. Now for the hydrogen atom, the energy level diagram shows the energy increases as the principal shell increases. So 1s has lower energy, then 2s and 2p, then 3s, 3p and 3d, then 4s, 4p, 4d and 4f. So 1s and 2s has more energy, 2s and 2p has slightly differ in their energies, then 3s have more energy than the 2s. So energy of orbitals in case of hydrogen atom depends only on the principal quantum number, that is n. It is 1, 2, 3, 4. So nothing else. In case of hydrogen and hydrogen-like atoms. Now, in case of multi-electron atoms, this picture slightly differs. So in that case, the 1s has lower energy, then 2s, then 2p, which has slightly more energy. Whereas in case of hydrogen, they have same energy, but here in case of multi-electron atoms, the 2s and 2p have slight difference in their energy. Then 3s has more energy, then 3p, then 4s. So there are some features of this multi-electron atoms. The first one is the same value of n. The higher the L value, more is the energy. It means 3s has lower energy than 3p, which has more energy than, which has still less energy than 3d. So as the value of L increases for the same n, so here the value of n is 3 in all these 3 cases, whereas the value of L increases 0 to 1, then 2. The energy increases, more the energy. for the same value of n, higher L value means more energy. Okay. Now the next feature is the energy difference between S and P of a particular shell is small, whereas in case of P and D it is more. So in case of S and P subshells, the energy difference is quite small, like 2s in between 2s and 2p. We are talking about 2s and 2p, 3s and 3p. Where in case of 3p and 3d, this energy difference is comparatively more. Now, some orbitals belonging to lower energy shell present at the higher position. So here in this diagram, 4s is at the lower position than the 3d. Now, why it is so? There is a rule according to which these are arranged, and that rule is known as Bohr-Bury rule, which is also known as n plus L rule. So you can simply take it as where the value of n is 4. Here the value of n is 4, suppose, and we have 4s, and in another case n is equal to 3, and we take the orbital 3d. Now in case of hydrogen, we are simply choosing the value of n for assigning the relative energy of different subshells. But in case of multi-electron atoms, we cannot take directly the value of n to assign the relative energy to subshells. What we'll do, we'll apply this rule, Bohr's-Bury rule, which is n plus L rule. So here I take the example of 4s and 3d orbitals. So in case of 4s, n plus L is 4 plus 0, because s is equal to 0, L is equal to 0, then it is designated as s. So this is 4. And here in case of 3d, the n plus L will become 5, because the value of n is 3 and the value of d, which is representing L, is 2, and the total is 5. Now here the orbital with higher value of n plus L has higher energy associated with it. Has higher energy associated with it. Right. Now next is the other examples. This is the same example. Now, if the two orbitals have same value of n plus L, right? This is the second feature of Bohr-Bury. So in case of n plus L, one has higher value and one has lower value. The one with higher value has higher energy. The orbital with higher value of n plus L is of higher energy, simply. But in case if two orbitals have same value of n plus L, for example, here 4f and 4d, where n is 4 and L is 3. So L is 3, n is 4. And in second case, n is 5 and L is 2. This is 5d and 4f. So in both cases, the total is 7. Now in this case, we'll concentrate on main energy shell. The one with higher main energy shell is of higher energy. If n plus L values are same. If they are same. Okay. Now next is filling of orbitals in an atom. Now after studying quantum numbers, that means when you get the information, when you get the knowledge about the in, informations associated with the electrons, then the next task is to fill the to arrange the electrons in different energy shells. And this is based on certain rules. And this distribution is based on some certain rules. Okay. And this distribution is always done in ground state. Now, what is ground state? The ground state is the state in which the electrons originally present at their lowest energy level. When the electrons are present in their lowest energy levels in an atom is known as atom is in its ground state. Electrons are in its ground state, okay, or normal state. Now, if they are at the higher position than their permitted values, then they are regarded as in excited states. They are regarded as in their excited states. Now, to distributing the electrons in the different orbitals, the first important rule is afbau principle. So, afbau means in German, afbau means building up. So, when we build up something, we start from the base, from the ground level. So, right, what is the rule? So, when we have to fill the electrons in the orbitals, we'll start filling the electrons from the lower energy subshell, and which is 1s, then 2s, then 2p. And by doing this, we have to follow n plus l rule. We have to follow n plus l rule to assign the energy values, right? We have to follow this. Okay. Next is paulis exclusion principle, which we already discussed, that no two electrons can have same spin in a orbital. So they must have opposite spin in an orbital. Next is Hund's rule. Now, in case of orbitals which are degenerate, like p orbital or d orbital. Now, in case of d subshell or p subshell, in p there are three orientations, it means three orbitals, and in case of d there are five orientations, it means five orbitals. So here the three orbitals are degenerate, here five orbitals are in degeneracy. Degeneracy means they are in same energy, well, they have same energy values, levels. So what Hund's rule state? Hund's rule states in while filling of electrons in degenerate orbitals, we have to fill electrons singly first. It means in either either we have to fill upspin or downspin first. It is wrong to pair them in a single orbital. If more than one orbitals are there in degeneracy, we cannot fill two electrons in one orbital and keep one empty. While filling three electrons in a p subshell, px, py, and pz are in degeneracy. We cannot fill three with two in one spin and two with upspin and one downspin. So this is again wrong. So Hund's rule states that we have to first fill singly all the degenerate orbitals in one spin only, either upspin or downspin. After filling all the orbitals singly first, then we can pair. Now, if we have to fill four electrons here in this case, in same, so the fourth one will come here in opposite spin, or any of the other two. Then fifth, then sixth. So we have to fill singly first in case of degenerate orbitals. So only then we can pair up them. Now representation of the electronic configuration. So orbital electronic configuration. So here the atomic number is 1, So 1s, so 1 electron is there. 4, 1s, 2 electrons in 1s and 2 in 2s. So maximum 2 can come in 1. So s l is equal to 0. It has only one value of ml. So one orbital, one orientation. So 2 electron. Again 2s, l is equal to 0. ml is equal to 0, one orientation. Now in case of carbon, 6 electrons are there. So in case of 1s, 2 electrons, and 2s, 2 electrons, and in case of 2p. Now for p, l is equal to 1. It means ml has values 3, -1, 0, +1. So 3 orientations mean 3 orbitals. So the next 2, the remaining. So 2 are filled in 1s, 2 filled in 2s. So -4, remaining are 2. The remaining 2 will go in 2p. So likewise the other configurations. Neon 10 electrons, 10 atomic number, 10 electrons. So 1s2, 2s2, and 2p 6. So remember, for p there are 3 orbitals, for s only 1 orbital. So p l is equal to 1. So 3 orientations are there. Okay. Now there is an alternative way. This is an orbital electronic configuration. So we cannot draw boxes all the times to show the electronic distribution. So the other simple way to write the electronic configuration is here. And in this case, we have to write N, L, X. Now what is N? N is the principal shell. N representing principal shell. L representing subshell. S, P, D, F. And superscript electrons, and the superscript of L shows number of electrons.